Hi all, I am Anishma A, Assistant Professor, Department of Civil Engineering, Vedavyasa Institute of Technology. Here I am going to present a tech talk on wind performance on tall buildings and aerodynamic optimization technique. The tall buildings are the most famous landmark of cities, symbols of power, a mark of national pride, and a confidence in technology. The economic growth, technological advancement, and scarcity of land, etc., have increased the demand for tall buildings. The most important factor that affects the tall buildings is wind. The tall buildings are often liable to excessive motion during wind events that can cause occupant discomfort and reduce the overall appeal of the structure. The wind can create excessive building motions. The dynamic nature of the wind is a critical issue, negatively affecting the occupancy, discomfort, and serviceability. From the design point of view, not only the wind load, the wind induced building motions are also within the scope of design to ensure building serviceability. It is well known that the behavior of wind response is largely determined by building shapes. The effect of wind varies with the time and space. So, due to the unpredictable behavior of wind, it is necessary to design the tall structures by considering the critical effect of wind on the tall structures. The aerodynamic modifications on the building can reduce the influence of wind load. Aerodynamic forces on tall buildings. The development in the construction technology and the social demand for tall structures have created a recent trend for tall structures. The structural safety of tall buildings is often dependent by the structural design to withstand wind load, whereas the habitability of the building is often hindered with the wind-induced vibrations. The height of the building and the wind velocity is directly proportional to each other. Under the action of wind, the tall buildings can oscillate. So, the effect of aerodynamic forces on the building damages the structural elements, reduce the life, and also create crack formation, etc. And also, due to this, excessive building motions can also be created. Now, the types of wind acting on tall buildings. The tall buildings are wind sensitive structures, so lateral wind load imposed on the building are governing factors in their structural design. The wind acting on the buildings are along wind, across wind, and torsional wind. The along wind deflects in the direction of wind. In the case of across wind, deflect in the direction normal to the direction of wind. And the torsional deflection, which are due to the non-uniform wind pressure over the surface of the building. For most super tall buildings, it is often found that across dynamic response dominates the wind load and sometimes causes excessive motion in terms of building serviceability and criteria, while the along wind force spectrum mainly reflects the approaching wind turbulence properties. The across wind force spectrum is largely determined by the flow separation and vortex form called signature turbulence. Along wind response. The along wind response acts in the direction of mean flow. The along wind occurs due to the static motion of the wind. Static wind effect primarily causes bending and twisting of the building. The movement of building is along the wind direction. The wind motion primarily results from the pressure fluctuations on windward and leeward phases and generally follow fluctuations in approaching low. Across wind response. The term across wind is used to refer the transverse wind. The across wind acts perpendicular to the direction of mean flow of the wind. It occurs due to the dynamic motion of wind. For tall buildings, wind gusts causes fluctuating forces on the structure which induce large dynamic motions including oscillations. The building is across the wind direction. The across wind response often dominates over the along wind response. The common source of across wind motion is associated with water shedding. The across wind oscillates can be excessive if building has low damping. When a building is subjected to wind flow, the originally parallel wind stream lines are displaced on both transverse side of the building, and the force produced on these sides are called as vortex shedding. The vortex shedding is an oscillating flow taken place when the air flow and obstructed by a body at certain velocity. The vortex shedding depends upon the two types of frequency. First one, the fundamental frequency of building, and the second one, frequency at which the vortices are shedded. When these frequencies coincide each other, then the resonance occurs, causing excessive oscillations in transverse direction, and thus the entire structure vibrates and causes failure to the structure. Next one is torsional wind response. The torsional motion is developed due to the imbalance in the instantaneous pressure distribution on each of the face of the building. If the distance between elastic center of the structure and aerodynamic center is large, the structure is subjected to torsional moments that may significantly affect the structural design. The torsional wind has significance by depending upon the geometry and the structural system of the building. Now, comparing along wind response with across wind, the across wind is more sensitive to wind speed. At lower wind speed, the along winds normally dominate, but with the increase of wind speed, the across wind take over. Now we are moving on to wind tunnel test. Wind tunnel testing is a powerful tool that allows engineers to determine the nature and intensity of wind forces acting on a complex structure. Wind tunnel testing is particularly useful when the complexity of the structure and the surrounding terrain resulting in complex wind flow. The test predicts the wind loads and response of structure, structural components and cladding to a variety of wind conditions. As the height of the building increases, wind load become increasingly important and efficient and reliable design. It is common to conduct a wind tunnel test for tall buildings having high aspect ratio, that means ratio of width to height. The size of the building and wind tunnel determine the scale of the model. It consists of a rotating platform, tripboard and spikes. Test involves the blowing of air onto the building model at various angles. The figure represents the wind tunnel testing laboratory at University of Florida, and the next figure represents the model of wind tunnels testing of Burj Khalifa in the scale of 1:500. Now we are moving on to aerodynamic optimization modifications which can be done on a structure. A tall building can be defined as a mast anchored in the ground, bending and swaying in the wind. The velocity of wind increases with increase in height. As a result of this, wind effects on the tall buildings. It is an approach that is normally taken in a situation when buildings' aerodynamics mitigations are found to be necessary, but only limited shape changes can be permitted in order to keep the building overall concept unaffected. Based on the impact of modification on the outer architecture of the main structure, aerodynamic modification can be categorized into two: minor modifications and major modifications. The figure represents the flowchart of modification. Minor modifications are aerodynamic one which to a minor extent affect the structural and architectural design. The modification to corner geometry, chamfered corners or corner cut, corner recession, slotted corners, corner roundness through opening, fitting of fins and vent fins are affiliated to such modifications. On the other hand, major modifications are aerodynamic one which considerably affect the structural and architectural concept. Examples of major modifications are belongs to the modification of tall buildings shapes, addition of openings, and vertical or horizontal slots to the buildings, and twisting or rotating of building, setback and tapering. Minor modifications. This types of modifications shows negligible effect on the structural and architectural concept of buildings. These are fins and vents, a slotted corner, cambered corner, roundness. Fins and vented fins. The basic square or rectangular shape of building is modified using small fins or vented fins. These act as a screening system. It decreases the across wind response because of the increase in the projected area perpendicular to the wind. Next one is slotted corner. Very effective modification technique to reduce along and across wind. Slots at the corners allow bleeding the air through it. Next one, chamfered corner. The along wind fluctuations force not affected much. These modifications are effective for reduction in the across wind fluctuations for a low angle of intensity. Corner recession effectively reduces both the along wind and across wind response. This modification is similar to the chamfered corner. This can be done in single, double or triple form. Next one is roundness. Most effective type corner modification. This modification changes the geometry to circular cylinder shape that is very efficient against wind. For the maximum across wind response, corner roundness is found to be more effective in resisting the response. It is a cost effective method also. These are the figures of corner modifications. Now we are moving to major modifications. This type of modification shows considerable effects on the structural and architectural concept of building. These are the classifications. Taper and setback modification. This modification has more significant effect in the across wind than in along wind response. This is a method of reducing the floor area gradually towards the top. The vortices will shed at the different frequencies at different height because vortex shedding frequency is inversely proportional to building width. The mass of the building will concentrate on the lower floors. Twisting modifications. Twisted buildings are effective in reducing vortex shedding along the height of the building. This modification is done by providing twisted angles, mainly 120 degree, and the effectiveness of twisting increases with increase in the twisted angle. Next is additional opening. This modification is done by providing openings or pores at the section of building. It reduces the across wind response. This allows the air to bleed into the building through the openings. This is the figures representing major modifications. Now we can go through case studies. First one is Burj Khalifa. You all will be familiar with this one. Burj Khalifa is the world's tallest building, which is having an height of 829.8 meter and a floor area of 3,09,473 meters square. The floor count is 154 plus 9. The aerodynamic optimization technique is tapering and setback corner modification. This modification shows effective in damping the wind response. The setback reduces the plan area throughout the height, and the number and spacing of setback changes the shape of wings on the tower. This is the modification in Burj Khalifa, and the shape and size and height are mentioned in this. The modification will reduce the vortex shedding over the height of the tower. Next one is Tapea 101. It is located at Tapea, Taiwan. It is having a height of 508 meter and having a floor of 101 plus 5. The aerodynamic optimization technique used in this Tapea is setback and tapering. Next one is Shanghai Tower, located at Padgong District, Shanghai. It is having an 80,000 meter square area and a height of 632 meter, having a floor of 128 plus 5. And the aerodynamic optimization technique used in this is tapering profile, twisting and rounded corners. It is in rectangular shape. The curved corners of the triangular cross section act to minimize the wind load, and 120-degree turning is adapted. The shape of the building reduces the wind load effect, and the wind flow around the building is completely different way. This is the plan and cross section of the Shanghai Tower. So now we are moving on to the conclusion part of our session. The wind-induced load and motion typically governs the design of lateral load-resisting system in tall buildings. Aerodynamic optimization is aimed to solve the structural resistance against wind. So, appropriate modification in the building can reduce the effect of aerodynamic forces. It is important to have a reasonable assessment of effectiveness of various aerodynamic options in the early design stage so that the potential pros and cons can be evaluated in the decision making process. Thank you all.